Us to the latest instalment of the IOP West Midlands Keele Physics Centre lecture series, evening talk series. So for those that haven't attended before, or perhaps haven't been for a little while, just a couple of housekeeping points. First and foremost, welcome. Thank you for giving up an hour or so of your evening to listen to a little bit more about topical physics and engineering. But just to give you a couple of pointers. So this evening's talk, and I'll introduce our speaker very shortly, will last around 45 to 60 minutes. And at the end of that talk, we allow you to ask some questions. So please use the question and answer function that you might find if you're on a laptop or a PC towards the bottom of your screen. If you're on your phone, it might be down on one of the sidebars. So please, if you've got any questions at any point, drop them in there and I will do my very best to ask them of Tianning later after the talk has completed. You may also be aware that this is the penultimate talk in our series this year. The next talk and our final talk is taking place on the 20th of April and is being delivered by Dr. John Mansfield of the University of Michigan. So if you're interested in cultural artifacts and how we characterize those, that may very well be a talk you don't want to miss. So with no further ado, I'm going to very briefly introduce you to tonight's guest speaker, and that is Tianning Xu. And Tianning is an experienced engineering lead who has worked in a number of companies, one of the largest, in fact, in terms of electric mobility charging solutions. And so it will come as no surprise to you this evening, ladies and gentlemen, that this evening's talk is on the topic of electric vehicle charging. So with no further ado, I'm going to hand over to Tianning, and with a warm, if you were in person, Tianning, a warm round of applause from our Keele Physics Centre. So over to you, Tianning. Thank you.
Thank you, Scott, and thank you for everyone who are able to come to join my presentation today. So the first thing I'm going to do is I'm going to share my screen so you can see the slide. So just bear with me. Hold on, just 1 second. Right, okay. I hope that you can see my full slide screen now. If there's any problem, please let me know. So today I'm honored to come to give a quick presentation with regard to electrical vehicle charging because I've worked in this industry for the last nearly 3 years. Let me quickly introduce myself. So my name is Tianning Xu, as what Scott has already introduced me. So I received my PhD degree at Nottingham University back in 2009. That was a long time ago. My background was about power electronics and the drives. So I have been working, learning and working on this subject for all my career so far. So I joined ChargePoint back to mid of 2020, which is one of the largest EV charging infrastructure providers. So I worked there for 3 years. I have recently left the company, and now I'm in a transition to my next job at the moment. Before ChargePoint, I worked in General Electric for nearly 11 years. Actually, that was the place where I met Mike Bowden, who is also online at the moment. General Electric was all about transmission and distribution where I was working there. So as you could see from the two pictures here, the top corner is representing ChargePoint, which I worked there. This is actually one of their DC chargers. I will talk about that later on. And then you can see on the bottom right corner is one of the typical pictures about the voltage sourced HVDC converters. So you can see that I've worked in two completely different animals, but both of them are quite interesting in my career. And I also worked in a company called Delta Electronics when I was still in China. And that is a company which is providing all the power supplies, adapters, and all this stuff. So very, very brief introduction about myself. Now let's move on. So I was actually thinking of asking everyone to put your hands up with regard to whether you have actually got any opportunity to drive an electrical vehicle or use the electrical vehicle chargers. But since we are all online at the moment, so I'm not going to do that. So let me quickly talk a little bit about electrical vehicle supply equipment. This is why we call it EVSE, because EV is electrical vehicle, EVSE is electrical vehicle supply equipment. If you want to make it simple, basically it's EV chargers. And as you probably know that this is one of the hottest topics in the last few years, because a lot of government, they were trying to accelerate the electrification across their own countries. This including North America, Europe, China. So this is happening really fast. If we use UK as an example, you can see that UK has given the policy that by 2030, their aim is to end the sale of the new petrol and diesel vehicles. And by 2035, is basically to make sure that all the new cars and vans, they have fully zero emissions. So this is a quite ambitious target. This has actually pushed the EV market to grow really fast in the last 5 to 10 years. So if you look at the chart below it, you can see that which tells you how fast the EV is actually being increased across different countries. Europe obviously is not the fastest. China is probably leading at the moment, but Europe is picking up really quickly, even faster than US. But the interesting fact here is that if you look at the right-hand side, this is basically is a snapshot of a report that I took from somewhere. That was actually old news, even though the fact still stays, which is talking about how fast the EV has been increasing, but how EV chargers been struggling to catch up. So if you look at the numbers here, you can see that in the 3 years between 2018 to 2020, basically all the electrical vehicles has increased by 110%. However, the EV chargers has only increased by just 58%. So this is why when you hear someone talking about range anxiety, that probably is one of the reasons, is if you don't have enough facilities or infrastructures to support the growth of EV, that is where people will feel reluctant to move into the electrical vehicles. But you could argue that it's a chicken and egg, right? Sometimes you need the facility to be there at first before you consider buying an EV, or sometimes when the EV number is going up really quickly, then that is where the opportunity has been created for all the companies to jump into this industry to try to build more EV chargers. So I will talk a little bit about the EV chargers. Today, I'm not going to talk about any EV specifically. This is probably the only page I will talk about electrical vehicles. And I guess probably if you are interested into electrical vehicles, you'll probably know more than me about everything to do with electrical vehicles. So there are all different types of electrical vehicles here. So if we want to make it simple, basically there are 3 major types. One is hybrid electrical vehicles. The middle one is plug-in hybrid electrical vehicles. And the final one is the pure or the battery electrical vehicles. Basically, this just tells you how electrical vehicles has been evolving from the ICE vehicle, the internal combustion engine vehicle, gradually moving into a battery electrical vehicle. So at the very beginning, for the hybrid ones, obviously, the industry or the car companies have put a relatively small battery there, small motor there as well, electrical motor there as well, which is able to share that burden with the gasoline motor. But the range is very, very small. We're talking about probably only 2 to 3 miles. And the way how it's being charged is based on the regenerative energy that is created every time when you're trying to brake the vehicle. But the middle one, obviously, is definitely a major improvement, because this is where the vehicle has provided you a place to plug in. So whenever you can plug in, that means you can actually charge the vehicle to a certain extent. This is why for the plug-in hybrid electrical vehicle, they started to have a much larger size of batteries, but still the combustion engine is still being used. So basically it's like 50-50, they share that burden. But when you move on to the pure battery electrical vehicles, that is where you don't need any combustion engines. So basically the home powertrain is like you have a huge battery below the vehicle and going through the inverter, going through the motor, of course, you have a lot of other accessories around the vehicle as well. So I've given some lists or typical examples of the cars below each category. If you pay attention to what's going on in the car manufacturer at the moment, like Tesla, obviously, is something very, very famous and well known, and their sales has been leading ahead of many other car manufacturers at the moment on battery electrical vehicle. Volkswagen probably is one of the European car manufacturers which has done very well on the BEVs. Audi, Hyundai, BMW, and all other large car manufacturers, they are all gradually transit into the pure electrical vehicles. And they know that they have to do that, even though they probably don't want that to happen so fast because of their existing production plant, as well as a lot of other commercial related reasons. But they know this is coming, so they have to put all the R&D onto that to try to help on this acceleration. Otherwise, when we actually move into the battery electrical vehicles, if you are actually left behind, then you wouldn't be able to get enough shares of this market to like when you're doing on combustion engine vehicles. And as you could also imagine that the emission would be different as well. So the aim obviously for us, like in UK by 2035, is to all move into the battery electrical vehicles. That means we will end up with completely zero emissions. Then talking a little bit about electrical vehicle supply equipment, i.e. the EV chargers. So basically, as I mentioned, I'm not going to deep dive into anything on the electrical vehicle, but I will focus more on the charger itself today. So chargers have a different type of category as well, if you have ever used any chargers in the past. North America and Europe, they basically have divided the chargers into different groups, but fundamentally they are the same. So if you look at the top ones, you can see that as defined by SAE J1772, basically is a standard for North America. They basically have divided the chargers into 3 levels: AC level 1, AC level 2, and DC fast chargers. And when you move on to Europe, which is more regulated by IEC standard, they have mode 1, mode 2, mode 3, mode 4. So basically mode 4, mode 3 and AC level 2 are the same, mode 4 and DC fast charger are the same. And it's just in Europe, they have made it more lower granularity, where they have mode 1 and mode 2, which corresponding to the AC level 1. I'm not going to go through the whole table line by line. I believe that when you got an opportunity to come back to look at this video again, you will be able to find all the content. So basically, they are trying to define the mode or the AC level or the DC level based on 2 things. One thing is about the power level. As you could see that when we are moving from the left hand to right hand, the power level basically has increased massively. For example, if we use Europe as an example, the mode 1 is only 16 amp, single phase. Then it will gradually move into still single phase. They will come with a control palette. This control palette is very important, as well as a shock protection, because if you just plug the cord into the wall, that basically means that you wouldn't have any protection there. However, if you have that control palette and the shock protection cord, which means that this has increased the safety of your charging experience. And both of the mode 1 and mode 2, you basically can plug in at your home with a normal socket. You don't necessarily need anything special. All the household AC socket can do the job. That basically means that if you get an EV tomorrow, you don't actually need to buy an EV charger. You can just simply plug in and then you will start to charge your car. And normally most of the EVs, they provide you with that cable. However, the charging experience won't be super pleasant because it will typically take 8 to 12 hours. If you buy a Tesla, for example, because the range is really long, then the charging time can go even further, maybe 24 hours. So obviously that is not the way we want to be, right? So mode 3 is much more practical because it started with the same voltage, but the current increased to 32 amp. That basically means the power we're talking about is typically 7 kilowatts at your home. So for example, at my home, I've got an EV charger. I've got EV as well. It's 7 kilowatt. My EV hasn't got a long range. However, if you charge with your charger, it will only take like 4 or 5 hours to get it from 0% to 110%, 100% state of charge. If you have a longer range EV, that will only take you 7-8 hours as well, maximum. That basically means that overnight time, when you are sleeping, your EV is being charged. The next day when you wake up, the EV is ready for you to drive. DC charger, of course, is something also very popular. Normally, of course, no one will install DC charger at home. But DC charger is very popular to be used as a public charger or will be used on the motorway. When you go to the service, you don't want to dwell there for too long, only half an hour. You want to use DC charger to fastly charge your car. And DC charger doesn't go through the onboard chargers. So all the AC charger basically to charge your car, that means the AC power coming from the grid, they will go to an onboard charger on your car. And that onboard charger will change the AC into the DC to charge your battery, because battery obviously is DC. However, for the DC charger, they don't have to do this. The DC charger itself has already converted the AC power into the DC, and then it will charge your battery directly. And the current will be relatively high as well. However, it is not recommended to use DC very often because of that high current. Normally the battery will get heating issues. So it's not like that. You've got an EV that you should use DC charger constantly, let alone the price of using DC charger is going to be high as well. So it won't be that economic as well. But obviously the benefit is that it take only half an hour to 60 minutes to charge to 80%. If you look at the EV charger, different type of sockets, you can see that there are quite a lot of difference as well. I think this is one of the challenges in this industry, because when loads of countries or the companies started to do the electrification, obviously they all developed their own standard. In North America, they have Type 1 and the CCS1. CCS basically means the combined charging system. As you could see that at the upper part of the plug is similar to the AC, and the lower one just the plus, DC plus and the minus. Europe has a different one, which has a Type 2 and CCS2. The reason why they are different is because in North America it's normally single phase, but in Europe it's 3-phase. So this is why it have 2 more pins here. Japan has developed their own ones, especially this one called CHAdeMO. It's mainly developed by Mitsubishi and Nissan. But at the moment, loads of countries, they started to retire this socket. So you're going to see this CHAdeMO socket less and less in the future. China has a completely different system, which is a nightmare as well. So if we, for example, want to sell chargers in China, we have to completely change our socket systems. Otherwise, the charger won't work. The most interesting fact is that Tesla has come up with their own plugs. And actually that product is pretty good compared to CCS1 and CCS2. It's exactly the same, no matter whether you use it for DC and AC. It's lighter as well. But the problem is that they didn't open their network to most of the EV drivers in the past, or non-Tesla EV drivers in the past. So this is why they started to become their own, they built their own kingdom. So now they started to realize that. So they started to open their network in North America to more non-Tesla drivers to use their chargers. In Europe, if you want to use it, basically you just use an adapter. If you have an adapter, then you can just plug in, and then there won't be any problem. So this is a very quick snapshot about different type of chargers as well as different type of their plugs. And then you can already see that there are quite lots of differences here already. Then we're talking a little bit about the EV charger applications. So basically the EV chargers has so many different categories, but how actually they are going to be applied across all different applications. I've mentioned some of this already in the previous slide, but obviously this slide can give you more idea about that. So this is actually retrieved from one of the reports which has summarized this quite well. If you look at quite lots of locations, unlike the previous ICE vehicles where you normally top up your fuels just at the petrol or diesel stations, for the EV charger, the way is going to be completely different. So the reason is actually very simple. The EV charger can be installed in many different places. So for example, you can install the EV charger at your home, no matter it's a single family home or a multi-family, for example, like the apartment. It can be installed at a workplace because normally when people go to work, they normally will stay there for at least 7-8 hours. So that would be the brilliant opportunity to actually top up your vehicle. There will be destination as well, where you, for example, go to the cinemas, you go to do some groceries, or you just go to a park, want to have a Sunday roast. You stay there for at least 2 hours or even more. So that would be another opportunity to charge up your car. On the go means that if you're going somewhere, especially if you're using a road or motorway, that is where, of course, you are going to sometimes need to top up your vehicle halfway through. But that's not a big problem because you need to go to the service because of different sorts of reasons anyway. But you wouldn't stay there for too long. So you need normally a charger which is fast enough to top up your car. And there's also another one which people probably don't think too much about, but actually that represents a very high market share, which is we call it fleet. As you could imagine, the buses, the taxis, all those Royal Mail vehicles, Amazon vehicles. So this is what we call the fleet, and the fleet needs to be electrified as well because they are constantly on the road, and they are actually one of the major vehicle groups which create quite a lot of CO2 out there. So they also needs to be electrified. But they obviously, depending on the application, depending on the type of vehicles, they can use different sorts of chargers here as well. So, but basically, this just tells you across all these different applications and the locations how the different type of chargers I mentioned in the previous slide can be applied there. Normally, obviously, for home, you don't need a big one. So you only need an AC charger, a single phase, 7.4 kilowatt. That would be sufficient. Workplace, normally they will install single phase or 3-phase AC chargers because you stay there long enough. You don't need a DC charger. For the destination and on the go, I think it's a mixture of both, especially for the destination. You can have both single AC charger and DC charger. On the go, normally it's DC charger, but sometimes you can also see some DC charger as well, AC chargers as well, because DC charger is normally more expensive. And the fleet is a mix of all of them. So, as I mentioned in last slide, is that when people is driving EV, when you're trying to fuel your EV, the behavior becomes completely different. So very often people think, oh, how I'm going to actually stay at one location for that long time because the charging is much longer than just using the normal petrol stations. So this is why you're not going to stay there. You're not going to stand just next to your vehicle and wait until your vehicle is fully topped up. You normally will take all the chances when you're going to do different things to charge up your vehicles. When you're sleeping at home, you can charge up your vehicles. When you're going to work, park at your workplace, you can charge your vehicles. When you go to do the groceries, go to the cinemas, go to see any restaurants, that will be the brilliant opportunity to charge your vehicles. When you're going out of the town, on the motorway, you use the chargers at services as well. So this is why when we're trying to install the chargers at all different sorts of places, we don't think too much about, we don't think too much like a group them just in very specific locations. We try to put them everywhere we can, because that will help to facilitate the transition into the EVs. That is where you can easily find the EV chargers whenever you need. And I believe that you have all seen this app called That Map. That Map basically is one of the largest EV cloud map, which is able to help you to track where the EV charger is. So you wouldn't need to use that in the past, right, when you were driving a petrol or diesel vehicle. But now you need, because the chargers is basically everywhere. So you need to know that where the charger is, which can hopefully help you to define your route when you want to go somewhere. But as I said before, that it doesn't necessarily mean that we are already there. We're not there yet. The EV charging points is still trying to catch up. So this is why people still have some hesitation to move into the EVs. But we are going to get there. That is going to happen sooner or later. If you look at this slide, you can see that the interesting fact is that even though people put lots of public chargers out there, 75% of the charging in the future are still going to happen more at your home or your workplace. That is where that is the reason why the home chargers or the chargers which we sell to the workplace is going to be the main volumes in this market. When everyone starts to own an EV in the future, most likely there will be EV charging facilities at your home or at the shared house or apartment that you are living in. It won't be so practical if you don't have that, because that basically means that you have to always go out to find somewhere else to charge your car. However, this doesn't mean that this will be good enough. You still need some public chargers, because you could be on your way, you could go somewhere, right? The car may be running out of batteries. You still need the public chargers, and you also still need those DC chargers which are on the motorway, which to help you to do the long distance. So just this slide basically is trying to hopefully deliver a message that let's forget about how we feel our car in the past. The way how we feel the car in the past stopped working anymore. For EV, the way how we do it is completely different. It's like how you top up your the battery of your phone, right? Whenever you got the opportunity to charge it, you will charge it. You wouldn't go to any specific place to do that. So coming to a little bit more real world, I know that I talked a little bit, quite lots of theories here. So let's have a look at the actual chargers. So there are quite lots of chargers in the market. I worked in ChargePoint in the past, but obviously I've already left the company. So I'm going to be very neutral here today. So there are different sorts of chargers in the market. If you go to Google to search it, you're going to find tons of them. But of course, there are one which are very expensive, very reliable. The charging company has put a lot of stuff in it, but there are also chargers which just basically transmit the AC power into your car, but don't do that much things in it. So basically, if you look at this, there are many ways to divide these groups. I divided it into two groups. One is a residential and a commercial group, which is mainly the AC chargers. The other one is purely commercial, which is DC charger, because normally people wouldn't install a very expensive DC charger at your home. And if you want to do that, you wouldn't have enough power to do that. On the AC side, there are two groups, as I mentioned in one of the previous slides. One is the home charger. So home charger here, for example, you can say we have the point charger, My Energy, Zappy charger. My Energy has been really popular recently. They are actually one of the British brand, which has done very well in the last few years. So this is their home charger, which can also actually be used as a public charger as well. The very right-hand one is the Wallbox charger, which is a Spanish company. So if you look at them, some of them are socket units, meaning that they don't come with a cable. So you have to bring your own cables. If you see something called BYOC, it means that bring your own cables. Personally, I don't like this, because I think that for the convenience of all the EV drivers, all the chargers should come with a cable, so you don't have to occupy your boot with a very bulky, long, probably dirty cables. But because of different reasons, there are loads of chargers which are just non-tethered, meaning that there's no cable on that. So you have to always have a cable in your back boot, just in case you have to use a charger like this. But there are chargers which already come with a cable, so that means it would be very handy. Just to unplug it, plug it to your car, and that'll be fun. There are lots of public AC chargers as well. So the first one is actually from ChargePoint, which they released last year. Very slim. You can have dual sockets there as well. You have got a screen on it as well. So you can charge two cars simultaneously with maximum 22 kilowatt per car. This one is from EV Box. And this one is actually interesting from this company, for Kempower. Kempower realized that there could be a lot of applications where you don't want to fix your chargers in the ground, or if you just want to temporarily charge your car, but you don't have the EV chargers. So they come up with wheeled ones. So basically, you have to plug one of the socket into the grid and put the other one into your car, and then you can charge the car. It doesn't come with any battery in it. So that means you cannot store any energy in advance. You still need to connect to the grid. But it's very handy because you don't have to do anything in advance to try to fix a charger in the ground. This normally won't be able to be used for the long-term purpose. It's normally for all those conditions where you just want to temporarily charge your car. This one is also interesting, coming from Ubitricity. This company is also part of Share Recharge now. So they basically leveraged all the lampposts. So one of the subjects in the past is all about how can we make the charger looks nice? Because when you install all those chargers, as I just mentioned, they are going to actually have some visual impact, right? If you design some charger that looks really nice, probably the visual impact will be less. But there are chargers which don't look so good. So like in London, if you go to London, you could already find loads of these chargers, which is just leveraged the lamppost there because the power is already good enough. The power won't be high, probably only 3.75 kilowatt or 7 kilowatt maximum. But normally if you park along the road for a few hours, that'll be good enough at least to top up like 40–50% of your car. Then coming to DC chargers, and then you can see that compared to the AC chargers, the DC is like a beast. It's much bigger, and the reason is simple. It's because in the AC charger there's no converter in it, no power electronics converter in it. It's normally just all the digital part. They still have the modem normally to communicate with the cloud. They have the payment systems. Sometimes they come with a screen. They have a bunch of contactors there as well. They have the breakers in it, maybe. They have meters in it, but they don't have converters. But for DC, it's different. You have to put the converters in it, the power electronics converters, to convert the AC into the DC. And depending on the power density of that DC charger, whether it's a 150 kilowatt DC charger or 300 kilowatt DC charger, the size will be different as well, because no matter how great you can make the power density, physics is physics, right? I believe you know all this better than me. So we have different sorts of options here as well. For example, what we call it integrated. Most of the DC chargers are the integrated ones, meaning that they have it's a DC charger. You put it there and you get the AC connected, then it will convert to DC, and then you can plug into your car directly. For example, this one is IOP. This one is Tritium, an Australia company. This one is coming from ABB. So the first two, they have very high power, but the last one is only, I think, 50 kilowatt or something around it. This is why they can still be hanging on the wall. There's also something called distributed ones. The way how I call it distributed is like the ChargePoint's Express Plus system or the ChemPower's S series. It's because they have a huge power block or power hub. All the converters are inside it. They convert the AC into DC, and the power is very high. We're talking about probably 200–300 kilowatt. And then they have all this distributed unit. When I was in ChargePoint, they call it power links. It's a similar here. ChemPower obviously has done a good job here. They have put this one really slim. They can put that across each fleet vehicles, and then all the powers coming from the main power hub are distributed across all these distributors. You might wondering why you want to do that. And one of the reasons is because for the fleet applications, like as I mentioned, the Royal Mail, the buses, when they come in to the site, what you want to do is that you want to park your car against the one chargers. And then over the nighttime or during daytime even, if you want to decide that which vehicle you want to charge first, or you want to charge them evenly, or which group of vehicle you want to charge first, that'll be very easy to do it, because you can decide whatever the power stored in this huge power block, how you want to distribute them across all those vehicles. So in overall, you'll be more economic, more flexible. May not be the best application for the public chargers, but for fleet, this is one of the selling points. The other one is called pantograph. I believe you probably all know pantograph, which has been used on the train system quite a lot. The pantograph basically is another way to top up the bus, which we call it the opportunity charging. So when you have those buses going around the cities, you can't guarantee that the battery inside those buses are good enough to support them for the whole day. And sometimes they get really busy. They don't have enough time to go back to the hub and stay there for a long time to trying to get top up. So one of the way to do it is sometimes they have to stay somewhere for 10 minutes or 5 minutes. That is where they get top up really quickly through this pantograph system. Basically, the power is in a block somewhere else, then going through this pantograph, and the bus driver don't have to do anything. They just press a button, and then this pantograph will come down or going up, and then they will finish all the communication, handshake, and then the power will come in. So this is just a quick slide talking about all different sorts of example chargers that you can find in the market. But if you go to search on Google, you're going to find probably another 50, 60, or even hundreds of different chargers. But fundamentally, they are the same if you look at how they're being grouped and divided. So obviously, my background is more on working with the engineers. So everything is about engineering, right? How you develop a EV charger and how you bring them to the world. So this is why I want to touch base a little bit about how we actually do the development and test. It's not something far different from when you're trying to develop some other industrial or power electronics product. Actually, the overall process is very similar compared to when I was working in GE on everything like infrastructure projects. In overall, it is divided into different groups. Like you start with requirements capturing, where you look at what this product actually means. What do you want? What the customer wants, and how the product should be defined. What kind of features you want to have in it. And normally you can't have everything. You have to really think through about the requirements, combining what your competitor is doing, what the market wants, and what you are able to deliver, and what your company want to differentiate yourself. So there are loads of things that needs to happen between the product management team, the marketing team, the engineering team to define this part. And once this is more or less there, then we're going to move into the conceptual design, where you start to look into different concepts which are able to meet this this requirement spec. And you also make use chance to do some architecture design as well. You also probably do some early proof of concept, because you want to make sure that whatever the concept you come up with, that is something that you can actually convert it into a product. So there will be a lot of trade-off exercise in this stage, because you very often find that, for example, you can realize certain electrical design, but you have to compromise certain mechanical design, or the other way around. So this is why sometimes the engineers coming from different disciplines, they constantly fighting with each other, because they all believe that in their own domain, the part which they are designing or developing is the most important. But we have to really look at this from the architectural point of view, and then really make sure that whatever the products we come up with, maybe it's not the perfect product, but at least it's the best product we could possibly do to meet the requirements. And then we'll move into the detailed design, where you do quite a lot of detailed design, prototyping, testing. You also need to look at the tool as well, because when you get into this stage, you have to consider, especially for the EV charging product, once it is released, it will get into a very high volume. So when you get into a manufacturer, you need to look at what kind of tooling that you're going to do to try to manufacture them. There will also, to try to de-risk your design, normally the company will start to do some pre-productions. They gradually increase the quantity. During the detailed design, they already, for example, produce 50 units. They're just trying to prove that actually the design is consistent, actually is manufacturable, everything still work. And then we'll also look into the manufacturing plan as well. And then you come to the validations. Validation is a very, very important stage. You do the test on the individual sub-assembly designs, individual circuit PCBs. You're also trying to gradually move upwards, going to the high level to do the full system validation test and make sure that the whole system actually works. Several interesting tests, which I think is worth mentioning here. One is called the interoperability test. This is something very special in EV charging industry, because as you could imagine, once the EV charger is out there, it has to got the ability to charge all the vehicles in the market. But sometimes because of how the vehicle has been designed, as well as how the software in the vehicle has been programmed, this may not always be the case. So this is why this interoperability test basically means that to test your charger with different type of vehicles. Normally we test 20+ vehicles to prove that your charger is actually able to work with a single-phase vehicle, 3-phase vehicle, and different power of vehicles as well, different brands of vehicles as well, different type of vehicle as well. The other one is called reliability test. I'm going to show you a quick page later on, which is, even though it's coming from ChargePoint, but it's actually public. Everyone can use Google or go into ChargePoint to find this page. And then there's something also very important called the regulatory certifications. I actually got another page to cover this. Why I want to specifically mention this is to actually show all of you that in the real world, how much work you actually need to do to bring a product into the actual market. It's not about, oh, you stay in the lab, you do something, you come up with great design, you then develop a prototype. That means that you can sell it to all the consumers. You can't. There are plenty of the things that you have to do before you can actually do that. And finally, obviously, is industrialization, where you have to look into how you want to produce it, what kind of end-of-line test kit that you actually need, and all the customer support. Because once a part is delivered to the site, you could constantly get problems, issues. Obviously, all this process is not a one-way process. It's always going back and forth. Sometimes you do a little bit of detailed design, you have to come to the concept again, you do the validation, you find problems, you come back to the design again, trying to redesign it, and then going to do the validation again. So I will probably show this page at the end if we still have time, because I'm a bit conscious of the time here. Regulations and the certifications. Again, this is just a snapshot of all the certifications we may have to do on the EV chargers. You could wonder, it's just an EV charger, why you want all this? Unfortunately, EV charger is a product which is going to sit out there being used by all the drivers. And it has to be safe, it has to be functional, and also it has to be able to not interfere with many other equipment which is around it. So I'm not going to go through this whole list, and then this is not an exhaustive list as well, by the way. I just want to highlight several things. In Europe, CE mark is something important because the UK is already not part of European Union. So we have to do something called UKCA in the near future. All this is governed by the IEC standard 61851. If you look at that standard, you can see that there are a very, very comprehensive list of requirements and tests that are required. One thing I want to highlight here is that all the EV chargers, even though they have all the electrical parts in it, like even the power electronics converting it, but one of the key things we all nowadays have in the EV charger is radio equipment, meaning that you have the modem in it, you have the all the cellular connections in it, you have Bluetooth in it. So all these things is because all these EV chargers becomes smarter and smarter. We want to connect them to the cloud. We want to connect them to the cloud so we can monitor them, we can have the information from those chargers, we know what's going on, we can generate a report. There's another page which covers this subject later on. But this also means that you have to do quite a lot of EMC tests. You have to make sure that your EV charger is not interfere with any other things around it. All EV charger have got the basic immunity to anything that come to you. One more thing I want to highlight is this thing called MID. So basically for all the public chargers, if they come with a meter, that means you have to pay for your charging. The government has put this there saying that you have to certify your charger against this standard to make sure that your meter is accurate enough to charge your customers, because they pay for whatever they used. So it have to be accurate enough. If your charger doesn't come with an MID, if you, let's say, install a charger somewhere and you've totally forgot about this, then what you're going to end up with is that your charger is going to be putting either the idle mode, meaning that it cannot be used, or if you are willing to do that, you can only let everyone to charge it by for free, because your meter is not fully certified to be able to let the customer to pay for it. So this is just give you a quite lot of snapshot about all the standards that are required across different continents, and that is what brings the challenge to all the EV charging companies, because especially like when I was working in ChargePoint, obviously we want to be the global leader of EV charger. We want to sell our chargers across all countries, but that basically means that you have to consider across all the continents, all the countries, what certification you have to do, how you're going to certify it, how you're going to make sure that your charger is compliant with the local regulations before you can actually sell your charger there. So very, very complex there. sometimes you can find that maybe you spend even less time on developing the actual product, but spend more time to certify it. Talking a little bit about app and the cloud, even though my background is power electronics, I'm not a software engineer, but I highly appreciate why this part is so important nowadays. As you know, that software is something that you cannot live without in everywhere, no matter it's a cloud or whether it's in the actual hardware product. You need software basically everywhere. So most of the chargers nowadays, they are relatively smart. They all, as I said, they've got either the Wi-Fi or cellular connection, which is able to be connected to the cloud, where then you can have either a web-based platform or your app, which is able to monitor the charger. But of course, from the company to company, they all have different features. Some of them are very comprehensive. Some of them are relatively simple. So for example, why we did this? So basically for station owners, for example, you can do the real-time visibility. You can check where we are on the charger, whether the charger is actually available or not, and whether the charger has been used by someone or not, if there's any problem on the charger. You can also have the controllership, but basically you can configure the charger in the way you like because you are the owner of that. For example, like at your workplace, the employer can define the price of all the chargers there. They can give it for free for all your employees. They can define a session length, meaning that you can use the charger for free for 2 hours, but after that you have to pay for it. They can also generate a report. They can look at the end of each month how many chargers has been used, how often they have been used. Then they can decide whether they need to install more chargers or not, because they may find out the chargers is not good, the number is not good enough, or maybe they found that the chargers is underutilized, so they may decide to open the chargers public or semi-public to others to come to use them. They can also do energy management. As you probably could imagine, that most of the sites, they may not come with enough powers. So this is where you probably want to spread your powers across all chargers, and that is something that you can configure on the cloud. Will be very useful for drivers as well. As I mentioned, nowadays, because of the range anxiety, the drivers really need to know where is the chargers. So all these apps is something that can be very helpful. I highly appreciate that nowadays, once you become an EV driver, you probably would be wondering which app you should use. There are plenty of apps that you can use. Not all the apps, unfortunately, can give you all the chargers. In UK, that map probably is one of the good ones. But if you go to different country, you have to download a different app. So this is why some of the companies are trying to make sure that they integrate as many chargers as possible onto their app. That basically means that in the future, if possible, you only need to use 1 or 2 apps. It's like how you use Airbnb or Booking.com to track all the hotels or accommodations. You don't have to go to too many different apps. And also the drivers obviously can use them to do something called tap and charge. You don't need to use any other card. It's like how you do the contactless payment. You can just use your mobile to enable the charging. You can also monitor your own energy usage as well. At your home, you want to say, for example, how many energy I've used every week, and how much you have to pay for that. You can also manage the payment. So all these things is actually, even though I can only give 1 page today about this, but actually they are very, very essential to accelerate the electrification, because it's only until you have this, you will find that, okay, this becomes really handy, because there are so much things that you can do to manage your chargers, to manage your charging experience. If you don't have this, that problems. So this is why, as I mentioned at the start of this presentation, EV charging is a completely different journey or experience compared to using the gasoline vehicles. You would never download an app to try to track where a gasoline station is. You will never download an app just trying to manage or monitor your fuel stations, the traditional fuel stations, right? But now with EV chargers, this completely changed how we charge, completely changed how we manage it. This will be my last slide, and if I have some spare time, I will go back to the web page I've just quoted just now, which could give you some interesting idea about how ChargePoint is doing the validation on their product. Talk a little bit about the power grid and the EV charger. because all the slides before was just about EV and EV charger. And then one of the questions might be raised is about, okay, we know that we want to install as many EV chargers as possible because of the range anxiety. We want to provide that convenience to all the EV drivers. However, do we really have the power to do that, right? Because all the infrastructure are already there. How many of them we have to upgrade to be able to do it? So talk a little bit about that. What's the EV charger's impact on the grid itself? So at first, it's obviously an additional load. Even though one single EV charger is not a huge power, we're talking about 7 kilowatt, 22 kilowatt. But when you started to pile them up across the country, across the continent, that is still a very huge load. And many infrastructures which we are having now, no matter it's a substation or transformers, they have only been equipped with a power that is good enough to give you another 10 or 20%. They can't give you another 50% or even 100%. So that is going to be a challenge on all the existing infrastructures. I will talk about some possible solutions on that, but let us be realistic on that. This is going to be a challenge on all the infrastructures. So this is why we couldn't simply say, you know what, I want to dig several holes there on that road because I want to install several chargers there. You can't do that. You have to at first do some assessment to find out if you have enough power to support that or not. And secondly, even if you can install the EV charging equipment, they will still have some kind of interactions with the grid. So, for example, you can inject harmonics. All the chargers, they are power electronics component. They go with a PFC, which is a power factor correction phase. Depending on the power devices you use here, they probably have a good, very low THD, or they probably is not that good if it's a poor charger. Then they can inject the harmonics into the grid. I think now with the EV charging industry becomes evolving, and there are loads of good EV chargers which have got the EMI filters. They are able to actually reduce that quite a lot. And of course, they have to also be compliant with the standard. So this is not a huge problem anymore. However, there are also something called interharmonics. Interharmonics is not the integral of the main harmonics of the fundamental frequency. For example, if it's a 50 hertz, then we're talking about if it's 100 hertz, 150 hertz, 200 hertz, they are the main harmonics, but the interharmonics could be anything between them. Even though the interharmonics generated by the EV charger or the EV is very, very small, but when you stack them up, let's say you have 10 or 20 chargers of it, if you stack them up, that is still not something you can completely ignore. So this is another possible issues from the EV chargers. There is something called supraharmonics, which is supraharmonics means it's 2 kilohertz to 150 kilohertz. And nowadays, because all the matter chargers or the electric vehicles, they want to make the power electronics as small as possible, then they start to increase the frequency. So all the devices has been constantly switching under a very, very high frequency. That is where those supraharmonics could be generated and injected back to the grid. The other thing is that all the EVs, according to the safety requirement, they come with something called protective earth. And then because of all the common mode noise, you tend to put a lot of like Y cap or X cap capacitors between the line to the ground. And basically those caps will be able to help to divert the noise away from the equipment. However, that will also generate more leakage current. And the leakage current is something which is a problem for all the human beings, and so that could be a safety problem, or even if that is not a huge problem, that can trip the RCD, which is a breaker to trying to protect all the devices from the leakage current. So you can cause nuisance trip as well. When you're using something, you end up with the breaker gets tripped, and then the car cannot be charged. And I have seen this problem in one of the sites I supported in the past. Basically, the breaker just gets tripped, and when they change the brand of the vehicle, suddenly all the problem is gone. It's just because the previous brand of the vehicle, the leakage current is relatively small. But the impact could be the other way around as well. When you come into the grid, the impact on the chargers, for example, the grid voltage is not pure sinusoidal waveforms, right? They have harmonics in it as well. Sometimes the grid could have dips or over voltage because of so many renewable source penetrated across the grid. And sometimes it could even have blackout. So all those voltage change fluctuation could affect the EV charger, because EV charger normally have a range of the input voltage. Even if it is AC EV charger, the onboard charger on the car will also be able to cope with certain range of input voltage. And if that input voltage changes too much, that will cause functional problems of the charging equipment. And the limited power is what I mentioned just now, is that the grid may not be able to give you the power you want. So what we can do about all these things? So one thing is about power and energy management. This is one of the hottest topics in the EV charging industry. It's all about how you actually manage your power. So give you a simple example here. If you are on a site, right, that site has got limited power, and you want to make sure that all the fundamental facilities will be satisfied before they are used to charge your vehicle. For example, lightings, air conditionings, heatings, and all this stuff. So there are those meters working with the cloud system, which is able to measure the consumption of that site on the buildings and everything, and make sure that all the energy that has coming from the grid or available for that site is allocated to that building at first. And all the remainings will be then given to the cars, because maintaining the building, the demand of that building is more essential than charging up your cars. And in that way, you can do both, and then also not go beyond whatever is required by the grid. Also, you can obviously install local renewable resource. If you have a solar panel there, of course, you don't need to count on the grid. You can generate the energy yourself, and then for any surplus energy, you can put it in the battery, or you can sell it back to the grid. This things sounds easy, right? But of course, when you go to the actual installation, it will take a lot of time, because you need to, for example, sometimes you need a DNO to give you the permission to do that. And also it takes lots of time to consider where you actually install your solar panel, where you actually install your battery. And then also you have to size them carefully as well, because you don't want to oversize them and end up with economic problems, but you don't want to undersize them, because you want to make sure that the power flow is being fully managed and controlled. V2G, basically vehicle to grid, is another hot topic recently as well. Basically just tells you can, because every car comes with a battery. So if the onboard charger is able to support the power going the other way around, meaning that all the cars can export their power back to the grid, that will give us even more flexibility to manage our power. But this technology, even though some of the car manufacturers is already able to support the V2G, but personally, I don't think this is there yet. This is still a long way to go, because for the transmission distribution industry, all the DNOs, utility companies, they have to come up with a protocol which will work for everyone. Otherwise, if everyone simply pump their energy back to the grid, I don't think it's something that the DNO is able to manage. I think at the moment it's already a challenge for them, because of the higher and higher renewable energy penetrations. So they have to be careful on all these things, not cause any problems. So basically, this is my slide. I will quickly show you this page, if you can see it. So again, it's not because I worked in the ChargePoint, as I like to promote anything to do with ChargePoint. It's a public page. It's a page everyone you can get onto the ChargePoint. You can find this page yourself. Actually, the reason why ChargePoint is making this page is trying to give you a good idea about how much things that you actually have to do to try to test or validate your unit. And ChargePoint has done a very good job on that, trying to really going through very comprehensive validations to trying to prove that charger they have developed is actually with a good quality and high reliability. This page basically is about what they call it advanced test facility, or we call it reliability test facility. Because whatever the product you come up with, no matter it's an EV charger or any equipment or anything, electrical equipment, you may think that you have come up with a very, very good design with all the good features, very good performance. However, if you put it outside in the environment, because of the crucial environment out there, if it can only work 3 days, or let's say three months, that is far from good enough, right? Because normally we would expect the lifetime of a heavy equipment to be at least 10 years. So the way why they have this facility, the reason why they have the facility is to actually check whether the charger is able to survive all different sorts of crucial conditions once they are actually being produced, manufactured, and they are actually out there. So for example, the first one is what we call the mechanical test. As you could see, they use a very heavy, huge ball to keep locking the charger and see how all this front panel is reacting. There's something called vibration drop test, because the charger, when during the transportation, that they could experience this kind of problems, or if they are in a country which can have earthquakes, that is where all these seismic problems can become an issue. So they constantly shake and drop the charger and just say whether the charger is still alive, whether the charger can still be working, right? This is another interesting one, because on one of the charge point chargers, they have something called swing arm. So basically, it's help the drivers to get the plugs into their car if the car is a little bit away from the charger. So that swing arm can be constantly used. So this test basically is to check after, let's say, 1,000 times or 2,000 times of the use, how the swing arm actually looks like. Is it compromised? Is it still okay? This can still be used for another 2,000 times. This is another interesting one. When you plug and unplug the charger, it's like on and off, on and off, on and off. As you could imagine, there could be thousands and thousands of times that will be used. And is it going to, like 10,000 times after it's being plugged and unplugged, there could be problem on that? But whether those pins can be compromised, that means you can't align them anymore. So this charger basically is they call it connector cycling test. It keep doing this automatic connecting and disconnecting, and then trying to find out how those connectors looks like after all this test. The final one I want to point out is, which is when I was in HVDC industry, we did quite a lot of similar things as well. It's we call environmental test, because the charger, they have to survive outside there. They could be sold to different sorts of countries in the world. So the humidity could be high, the temperature could be extreme. That could be even next to the sea, where the salt density would be high as well. And they are all electrical equipment, right? So they could be compromised because of all these conditions. So they put it into different chambers, or even this one, you can see that got all the salt spread everywhere to see if the charger can still survive. And then they have a very comprehensive method to calculate the lifetime of the charger based on the test result. So this is why they call it accelerated lifetime test. I think I finished everything. So I'm going to stop share for a minute. That's okay.
Thank you, Tianning. That was a fabulous. So I really appreciate that. And actually, it's generated quite a few questions in the Q&A. So I think we've got 5 questions, which is a lovely amount in the 10 minutes or so that we've got left. So yeah, going to ask them of you, and we're going to start. And thank you, Will. So you won't be aware of this, Tianning, but we have some very young members, of which Will, aged 15, is probably one of our youngest, and he always, bless him, messages in with a question. So thank you, Will. And the question is this: do EV batteries have limited recharge cycles? If so, how many times can they be charged before a significant loss in capacity?
So let's address this one by one. So EV chargers, they all have a recharge cycles. Normally, the lifetime of the EV charger is around 10 years. However, this is what we put normally in the data sheet or the spec, but they can actually survive much longer. But because, of course, we are all in this industry, right? This is not something we started 100 years ago. So we are all trying to understand better about the lifetime of our product. However, I think it is highly confident that most of the EV chargers can work more than 10 years on that. But this doesn't necessarily mean that a certain component or certain small things in the charger will not fail within 10 years or post 10 years. And also depending on how you service the charger once every year as well. So if you don't do anything about it, of course, it may fail faster. So I assume that question has nothing to do with the recharge cycle of the battery in the car, right? Because that is going to be a completely different subject.
Yeah, I think I think that's a really good point. I'm not sure. I think actually Will was asking about the batteries actually in the cars. Do you have a sense of
For the battery in the
yeah,
car, I don't have the exact number. Again, depending on how you charge the car. If you use the onboard charger most of the time, the lifetime will be normally much longer. I don't have the exact number of the. I think it would be like 20, 30,000 thousands of tons. But in the normal use of your car, of the battery, normally will be, I think, more than 10 years. And again, the EV is also the same like EV charger, because it has only been in the market for probably just over 10 years. So this is why we don't have enough data to prove that. This is why sometimes people is a bit cautious on buying the second-hand EV cars. But personally, I think that they can last longer, even if they can't, because of the state of the health is dropping after 10 years. The battery can still be changed. Of course, this will come with a cost. And the interesting fact is that when all those batteries being recycled, they can actually still be used for many other applications, because the state of health, even though it has dropped by 20%, the battery is still pretty good enough for many other lower level applications. So this is another reason why that industry becomes more and more popular, is to look into how to keep the life cycle, the total end-to-end life cycle of the battery as long as possible.
Brilliant. Thank you, Tim. That really comprehensive answer. I'm sure that Will take that away with him. Another question then. We're going to go towards the inverters, if that's all right. So some of the power electronics. T. Martins asked, what semiconductor technologies are used in the inverters? Is it silicon carbide, gallium nitride? What are you using, or what are you aware of being used in the inverters?
What I'm aware of, obviously, I haven't worked in the powertrain industry yet. In my previous careers, obviously, ChargePoint is more producing the EV chargers, but I think the principle is the same, because they are the EV charger is basically converted the AC into DC. So basically, they have the rectifier in it, they have the DC-DC converter in it. It's just when they get into pump into the battery, then you have to invert them. That is something that can be used by the motor. So normally they are still using IGBT or silicon carbide. Silicon carbide becomes more and more popular now because of its the benefit it comes with it. I believe you are all fully aware of that. The reason why there is this transition is because originally the silicon carbide was relatively expensive, but now with the price starting to drop, as well as the benefit the silicon carbide can bring to us, because it can switch at a relatively high frequency. That basically means that you can make the converter even more, even smaller with a very high power density. The GaN device, I'm not aware of any real commercial application at the moment for the inverter in the EV, but I have seen a paper the other day that there are already some research organizations. They have done a very good job to prove that the GaN device can be also another good choice for the EVs. The problem with GaN is that the power level is still not high enough. So this is why you end up with, you have to parallel or loads of them trying to cope with the power that you need. So it's still more for the relatively low power applications. For the EV, because of the power come with it, silicon carbide and IGBT are still the best choice.
Really interesting. Thank you, Tianning. That moves actually nicely onto a question from Edward Lee. And you mentioned vehicle to grid charging, V2G. So I'm just going to ask a question from Edward, which is, what additional EV and supply equipment is needed to enable grid demand management, charger throttling, and vehicle to grid charging? So what additional supply equipment is needed for that to adequately happen?
So it's a very interesting and good question. So at first, fundamentally, what is needed is that no matter it's an onboard charger or the EV charger, I mean, mainly the onboard charger actually it's the one in the EV charger, because the battery basically connects to the EV charger, and the EV charger is able to do that. So the main thing that is needed is to make sure that the device, the power electronics device used in the converter, in that power electronics converter, is bidirectional. Is to make sure that if you use diode, then it won't work, because the current can only go from one direction to the other direction. You need to use the device, like the active device like IGBT or silicon carbide, I just mentioned, silicon carbide, IGBT, to be able to cope with this bidirectional power commutation. So this is one thing from the power electronics point of view. The second one is also something very important, is about how you manage the power flow. This is where I mentioned about all those things on the cloud, is that you have to be really smart charger, which is able to see how the power is being pumped into your battery and how it is going back, and when you want to do that. Because all those power cycling could be potentially detrimental to your battery as well, because after you charge up your battery, you started to discharge it. You could have more cycling on your battery. So the battery management system in the car, how you control everything through your software platform based on how you want to power flow them, and all these things are very important. The last one, last but not the least, is also how we work with DNO on that. The DNO will define a protocol, I believe, in the near future once the V2G technology really becomes popular. They are going to define a protocol to define that when you are allowed to basically pump that power back to the grid. It's like if you want to install a solar panel at your home, if you want to sell your electricity back to the grid, you have to apply. For that. You have to fill a form called G98, G99 to get the permission to do that. And then the price will vary across the day. And so when you go to the vehicle, it will be the same. There will be the charger which supports that. There will be charger who cannot support that. And there will be the time when you can do it. There will be time when you can't do it.
Thank you, Tianning. That's really interesting. Thank you for that. We've got two final questions. So I'm going to ask, and unfortunately, this person's submitted it anonymously, but I think it's a really interesting question. So this particular person asks, how much additional grid power, either in gigawatts or in percentage terms, might be needed if all cars were EV? So presumably beyond 2030. Or would existing generation be sufficient using various management technologies? So if we were all to convert to EV tomorrow, would we have a grid problem?
I think it's a large question, right? How should I say this? It's like if you really want, you can use probably the existing grid power to electrify all the vehicles. But then what that means that no one can use the maximum power of the chargers. Probably only minimum amount of the powers. And when you all plug the cars into the chargers in your workplace, because everyone got an EV, then everyone will get the minimum amount of power from it. I personally don't believe we have sufficient power to support this at the moment. This is why there are loads of renewable. I mean, even if we have to be careful on this, right? Because people have been thinking about electrification, but electrification shouldn't just look at the electrical cars. Think about where the power is from. If the electricity is generated by the coal, by the gas, right? You could argue that that is still not sustainable enough because you are using polluted power to power up your clean cars, which is contradictory to what you actually want to do. So what we really want is, while we are trying to electrify cars, we're also trying to accelerate the generation of the renewable energies, like using the wind farms, the solar panels, and trying to go step by step together to make sure that all the electricity you're using, because you are increasing that demand, is not giving the burden to the government or to the country to ramp up their power production just by using the traditional fuels. They should also ramp up all their renewable fuels to be able to cope with that. So it's not a question, unfortunately, I can't answer with any number here in gigawatt or percent. Every country will be different. Every location will be different as well. But it will be I believe there will be still some shortfall there where the governments have something to do. This is why you can see the loads of if you go to a loads of fleet applications, they started to install solar panels. They don't want to just count on the power coming from the grid. And that will be very helpful, because when they install the solar panel, they also install the battery, and the battery can help on that. And the battery can also help on the grid as well, because the battery can do a lot of load shiftings. They can also provide reactive powers to compensate the grid, to help to support the grid. So all this is like a integrated system.
Superb, thank you, Tony. And that brings us beautifully onto our final question. In fact, you've answered the first part. So the question comes from Keshav, and he asked about the sort of do EVs not just pass the carbon emission problem further down the supply chain, which you've kind of alluded to there, which is great. But his final question is, how does that compare to, say, hydrogen cars? So do you think that EV vehicles are going to be the future, or will that be surpassed or maybe supplemented by other technologies such as hydrogen?
It's very interesting question, because before this presentation I was thinking what questions could be raised during my presentation, and I was actually thinking that this could be one of them. I'm not in any camp at the moment. I'm not the one who say, okay, it's either A or B, because I'm personally a believer that this world is made by many things, and they all have their own benefit and their own challenges, and so it's all depending on the applications. So hydrogen, obviously, the power density or the energy density, of course, is not as high as storing everything in the battery. So you could argue that sometimes it's not very practical, but there are lots of companies, especially in Japan, they are doing lots of research on that. They start to put it into the application as well. And also, if you want to transport those powers, you don't necessarily use a vehicle. I remember they put a post on the LinkedIn, which is very interesting, to basically tell everyone that because of the low energy density, that basically means that you need 10 vehicles or 10 lorries to transmit exactly the same amount of energy of hydrogen, where you only need one to transport the electricity. However, you don't do that, right? You use pipes. You use pipes to transport the hydrogen. So I'm not the expert on hydrogen. So I know that I believe that will still become one of the technologies in the future, but I don't believe it is going to be the mainstream. Personally, I think that the EVs will be the mainstream in the future to help everyone to electrify. And this is happening, right? This is not something we just predicted. This is the fact. If you just look at how many EVs which are already out there compared to the cars using the hydrogen, I think you can say this. But I'm not saying that the hydrogen is dead. The hydrogen will be another technology which can be very complementary and can also be used subject to the actual application and subject to the actual location as well.
Wonderful, thank you, Tianning. And that brings us, the timing's been immaculate, so thank you. On behalf of the whole of the IOP West Midlands Keele Physics Centre, I just wanted to pass on my thanks for a really interesting talk on a subject that I know a number of our members have asked for. So thank you very much, Tianning.
No problem.
Watching at home, as I said, that's our penultimate talk. There is one left on the 20th of April, being given by Dr. John Mansfield of the University of Michigan. As you may have gathered, given his location in the world, this will also be a virtual talk, but we are very much looking forward to a number of in-person talks again next term. So thank you everybody for watching. I hope you've enjoyed this evening. I've certainly learned more than one or two things, and I hope you have a wonderful evening, and we'll see you again next month. Thank you everybody. Bye for now.
Thank you. Have a good evening.